It's a pleasure to be here. Today we are seeing different forms of scaling in this workshop, right? So there is scale in terms of large models. I mean, we have now very huge deep learning models with billions of parameters. The scale in terms of the infrastructure, like how we are doing distributed training, sometimes possibly over lots of machines or lots of GPU cores. So what I want to show in this talk is scale in a different form, that is the dimensions, right? Like how we can also scale in terms of thinking of data, thinking of computations in many dimensions. And that's where tensors come into play. I mean, indeed, the term tensor, I guess, is a lot more popular now given the popularity of TensorFlow. But I want to go back to its algebraic roots and think about how the current linear algebra operations can be taken further with tensor algebra. And so you'll see all this work that I'll present today is open source. I'll also present some of the software frameworks to run these, as well as show how towards the end, SageMaker has some of these algorithms. So I think everybody here in the audience has taken a linear algebra class, so we are familiar with the starting dimensions, right? So zero-dimensional object is a scalar. If you have one dimension, that's a vector. And if you have two dimensions, that's a matrix. And anything further is a tensor. So tensor really is a generalization of matrices. We typically think of matrices as rows and columns, but that's more an array interpretation. You can also think of it as an operator. It's generally a linear operator, right, if you go back to your linear algebra class. And similarly, we can think of tensors as also operating on a space and what kind of operations they incorporate. And so this is like both these forms of thinking we'll see in this talk, how these many dimensions can incorporate the richness in the data, but also the computations on tensors can further enrich our current neural networks with possibly better architectures, better accuracy, or even more compact networks. So that's kind of the thinking. Like, so far we've used linear algebra extensively in our machine learning algorithms. If you think about any standard neural network architecture, right, whether it's convolution, whether it's a fully connected layer, they involve matrix operations, some form of matrix multiplication. And the question is that all there is to it, or can we further make these architectures richer? And that's where we'll see tensors are a natural form to further extend neural network architectures, as well as encode data that we encounter in different applications in better and richer forms. So let me make that more precise in the talk. So kind of the idea is why tensors are natural frameworks for machine learning is because the modern data has so many dimensions, right? So every dimension in the data can now naturally be a new dimension in our tensor, in our data structure. And that's not that hard to visualize. If you think of the image, there are the two dimensions, the width and the height of the image. And if you also have multiple channels like red, green, and blue, then you have the third channel. So in that sense, it's a three-dimensional object. If you think about video now, time is the fourth dimension. So you have a four-dimensional object, right? And now you could similarly think of data with multiple modalities. So you not only have images, but you also have text. An example application is visual question and answering. The input is both an image and a question, and based on that, you have to come up with an answer. So in this case, what are even the dimensions in data, right? I mean, that depends on how we encode the text. I mean, do we encode the text in terms of characters? Do we encode the text in terms of vocabulary, right? How do we represent our input text will determine how many dimensions, the input dimensions that are present in this application. And so as you see, in real applications, you will get data from different input sources, and they form different dimensions. So a natural way to have this as input to, let's say, a neural network architecture will be thinking in terms of it as a tensor. So, you can also use tensors to represent relationships in data. Not only the raw input data by itself, but really, how are different data dimensions related to one another, right? So, we are familiar with using matrices to have correlations and covariances, right? So it's a covariance matrix. If you have a random vector, you look at the correlation between the different entries of that random vector. What you get is a correlation matrix. And the formulation is simple, right? So if X is a random vector here, you're looking at the cross correlation between every two entries of X as well as the self correlation. And all such correlations can be put together in a matrix, right? So every ijth entry will be the corresponding correlation between the entries. And so this is very familiar to us to represent pairwise correlations. So if you have a Gaussian distributions, all you care about are pairwise correlations, and that is enough to fit your data. But then we know that most of the models will not be Gaussian, and Gaussian will not be a good enough assumption. And hence, we can go to higher order correlations, and that's where tensors are also useful. So if you want to now look at third order correlations in your data, so you have, again, a random vector X, and you're looking at the correlation of X with itself right up to third order, as well as between the different entries. And so now to represent this correlation, you need a tensor, right? So in this case, it's a third order tensor because we have, right, between every triplet of entries, we are recording the correlation. And so you can see here, from a matrix, there is a natural way to go to the tensor if we have to consider higher order correlations in our data. And especially if we have a large scale data, it becomes natural to not only think of pairwise correlations, which it's sufficient only for a Gaussian distribution, but also higher order correlations if we want to model richer relationships. And so that's another application of using tensors to think about higher order relationships in data. So that's kind of like the two aspects, right? One was like directly think about data itself as having many dimensions, and if we want to naturally encode these different dimensions, let's use tensor as the data structure to express that. And the other aspect is if you want to think about relationships in data, different correlations in the data, again, I can use tensor as a general object to record correlations of any order. Right, so ideally, we want to do something more with correlations, right? I mean, if you just compute the correlations by themselves, that may tell you a little bit, but ideally, there's like some machine learning downstream based on these correlations. And we'll see later in the talk how these correlations can be exploited to get some insights about the data. Right, so one example is topic modeling, where we want to extract topics from documents in an unsupervised way. We'll see how these correlations will help us do that. And so now that we saw that tensors can incorporate data in multiple dimensions as well as correlations of any order, the next question is, what kind of operations do we do on tensors? I mean, with matrices, we know the primitive is matrix multiplication, right? So we can multiply two matrices. Can we do the same with tensors? How do we do operations on tensors? So you can see visually that there is a nice generalization of matrix products to more dimensions. So what we want to do with a matrix here is if you multiply a vector on this side, that means we are taking linear combinations of columns. Right? That's a way to think about multiplying a matrix with a vector. And similarly, now if I want to multiply a third-order tensor with, say, even multiple vectors, I can now multiply vectors along 2 of its dimensions. What I'm doing now is taking multilinear combinations of these, what I call fibers, right? So they are columns of each of the matrix slices of this tensor. And similarly, now I can manipulate the tensor. And so more generally, you can transform any given tensor to a new tensor through these contractions, right? You can extend these vectors, in general, could be matrices. You can multiply them in different dimensions. You can contract them in different ways. And so that's what gives us a dictionary of operations that's very rich, right? With matrix, you can only multiply in 2 directions. With higher order tensors, now we can multiply along multiple dimensions. And you can multiply them with also higher order objects, right? So not only multiplying with vectors, you can multiply them with matrices, you can multiply them with tensors. So there's a very nice extensions of operations we can do in linear algebra to now tensor algebraic operations. And so the question is, how is this more effective? Right? So for one, what we'll see is, currently the neural network layers are only doing linear algebra operations. If we now expand that to also being able to do these richer operations, what benefits can we obtain? And that's what I'd like to show some examples in this talk on how we can come up with much more general frameworks for neural network architectures through thinking in the lens of tensor contractions. Yeah, so the standard neural network for computer vision, takes in the images, goes through some convolutional layers, and then goes through fully connected layers, right? So, but when we get to the fully connected layers, what we are doing is taking an object that's, in fact, 3-dimensional, right? So there is like the width and the height and the number of channels, but we are flattening it or making it into just a vector and multiplying it with a matrix and doing some nonlinearity and proceeding, right? So at this step, we are losing information of the 3-dimensional structure because we are doing this flattening operation. So one of the very first things that we thought about was, we can have an end-to-end operation of tensors itself, right? We can maintain the 3D structure throughout the neural network layers and ask how that can yield some benefits. So what we came up with was a new architecture where we will, in the fully connected layers, contract the 3-dimensional activations directly, right? So now there are 3 weight matrices along each of the dimension that we'll learn instead of just a single weight matrix. And also in the last layer, we'll do a tensor regression rather than just a plain matrix multiplication. And the idea of a tensor regression is, again, we can parameterize the weight tensor as well as a low-rank tensor. This form is called a Tucker form of the tensor. But the idea is we can hopefully have a more compact representation of the weights in this layer by using a tensor regression. And so that's the idea that, because we have input that's a 3-dimensional tensor, and in every layer we are having a 3-dimensional object as the output, we want to maintain that information throughout until the very end. And the hope is this can give rise to better architectures. So what we found was with this new architecture, we can get quite significant space saving without losing accuracy, like up to almost 65% with almost no reduction in accuracy. And the idea behind this is, right, you can control the rank in these layers. So you can say what kind of rank do I want this weight tensor to have? And how much should I contract my tensor in multiple layers here? So you're also controlling these hyperparameters, and so that you have room to control for the compactness of your network in newer ways now. Earlier, the only way to control for the number of parameters was the width of the network and the depth, right? But now we have more knobs to control. We can have the rank of this tensor, weight tensor. We can have the dimensions of these different weight matrices to contract the tensor. So this gives us much more handle in being able to maintain good accuracy while having a more compact network. And so that's one of the benefits we can see by using tensor operations in our neural network layers. So the framework we used for this is called Tensorly. This was first started by Jean Kosafi. He also interned with our group and further developed it. And the idea is, like as Jeff presented in the earlier talk, a TensorFlow, for instance, has really revolutionized deep learning. So having good software frameworks is very important, right? And Tensorly, I would say, is a nice user-friendly framework for combining tensor algebra operations with deep learning. So there's Pytorch, MXNet backends, as well as the standard NumPy backend. So with that, what you can do is you can now define different tensor layers and directly do backprop end-to-end. So it makes it very convenient to think of new operations, and you have this unified dictionary of operations available here in this library. So there's also example notebooks in the repository if you want to play with them. Just to give you one example very quickly, the idea is you can very easily set up the backend, whichever you like it to be. And in this example, we're looking at a Tucker form of the tensor. That's having a core tensor and factors, and you can specify what rank you want that to be. And what you can now do is attach gradients to all these variables and do the standard optimization with any optimizer you choose. So it becomes a very nice integration to existing deep learning frameworks in now being also able to explore the range of tensor operations in various neural network architectures. So we explored other aspects of what we can do with tensors, right? So the idea is matrix operations have been very highly optimized on different hardware platforms. There is the notion of BLAS of different levels, right? There's BLAS1 for vector-vector operations. There's BLAS2 for matrix vector operations, and BLAS3 for matrix-matrix operations. But now as we go to higher order tensors, in fact, there is a need for even higher BLAS operations. So here in this one example, if you have a third order tensor and you're multiplying with either a vector or a matrix here, this becomes now like a BLAS4 operation because you are now multiplying in higher dimensions. And so the question is, can we have even better primitives for such tensor operations that go beyond our current linear algebra? Right? So what's the challenge here? So you can always turn this tensor contraction. If you're only contracting the tensor in one of the dimension, it's still a linear operation. So with sufficient manipulation, you can in fact represent it as a matrix product. Right? In this example, we are looking at, this is the B is the tensor, A is the matrix, right? B is the third order, A is the second order. And we want to multiply it, this first dimension of A with the second dimension of B. So if you just rearrange it appropriately, right, in this way, and you combine these two dimensions together, that is, make this into a matrix, you can do this as a matrix multiplication. The challenge is, of course, like doing these steps of permutations, right? If you explicitly do the copy, this requires more memory and even more computation. In fact, a significant of the time can be spent just transposing these objects. And this is not something you want to do, right? For instance, if you ask for transpose of a matrix, right, it's done in place. That means the transpose is never explicitly computed with our current primitives. Similarly, you want in-place operations for tensors as well, where none of these transpositions are explicit, right? There's never new objects formed. And so this saves both memory and computation. And so one of the things which we explored was creating a new primitive for a range of these tensor contractions. So you could possibly contract the tensor in different possible dimensions, right? And how many of them can we do in place? It turns out that a large number of them we can still do in place by having a new primitive that we call Strided Batched GEMM. Without going into details, it turns out to be a special case of the batch GEMM operation. So GEMM stands for general matrix multiplication, and batch GEMM is a primitive that takes a whole batch of different matrices and multiplies them together, right? So instead of one single matrix multiplication, it has a batch of matrix multiplications. And what we found was the general batch GEMM had too much of overhead in terms of pointer allocation that was not needed for tensor contraction. So we specialized it and made it more efficient for tensor contractions. And this is now available in cuBLAS. So in CUDA, this is available for efficient multiplication. And it turns out, in terms of the performance, on Pascal hundreds and GPUs, the more modern family GPUs after that, that the performance is very close to a single GEMM operation. So if you recall earlier, I mentioned that if you did all the transpositions, right, you would be doing a single GEMM, a single matrix multiplication operation. So you cannot do better than this, right? It's like all this other overhead that we want to avoid. And by using this new primitive called Strided Batched GEMM, we come close to achieving the ideal case. And so that, to me, this is just the starting point. There's a lot of potential to think about very efficient tensor operations, right? As we kind of combine more dimensions together, there is more opportunities for efficient parallelizations, efficient BLAS primitives in a variety of different architectures. And of course, if you have sparsity, that makes it even more interesting. Even sparse linear algebra by itself is a lot of challenges. And now if you go to tensors, it becomes even harder to design good frameworks for that. And that's something we haven't looked at so far. So there are other forms that you can use tensors in, right? As I said, time is now another dimension, right? So you have some observations in each time point, and now you have to think about how to do forecasting in time series efficiently. And this is a very challenging problem because you can have long-term dependencies, and there can be a lot of chaotic behavior, right? So even a little bit of a change can have very different behavior onwards. So how do we model something like this? Intuitively, we know that higher order correlations will be present in such highly chaotic time series especially. So tensors, again, seem like a natural framework to incorporate higher order correlations for better forecasting. And that's what we explored by tensorizing recurrent neural networks and LSTMs. Right? So a standard recurrent neural network, what it does is it maintains a state and then it propagates that forward. Right? So there is new input and there is a new output that you want to predict, but it's a certain state that you're propagating in forward. So you could think of it as a first order Markov because this state is all that matters to propagate forward, right? You ignore everything that you want to know about the past is incorporated into this state. But then, you can also think of a higher order model where you also take the past states and kind of incorporate them together. Right? In fact, you can look at the correlations between the different states in the past and put them together and try to make a decision for forecasting based on all these correlations between the past states. Of course, this would blow up the dimension, so you don't want to do it as it is. And so what we explored was a new form of, new form in this context, called the Tensor-Train formulation. And what it does is it trains to maintain a low rank approximation of this high order tensor. so that you're not blowing up the dimensions. It still has a reasonable number of parameters in your recurrent neural network. And so this tensor train kind of goes forward as a chain and tries to find low-rank approximations while trying to maintain the polynomial high-order correlations. And so this tensor train layer, you can incorporate it into your recurrent neural network, and we can do the same with LSTMs, right? In the LSTM cells, you can do the tensorization. And what we found by doing this was it can give rise to much better long-term forecasting compared to the standard LSTMs. So one was the traffic data set. This is one of the benchmarks for forecasting, where you want to predict the traffic in the next 2 hours, in the next 4 hours, and so on, right? So you want to predict way into the future. I mean, indeed, in this case, it's a few hours. And you can see that for the LSTM, right, the error especially kind of increases when it's beyond, like, let's say, this 12-hour mark, for instance, right? The error kind of increases a lot. Whereas for the tensorized LSTM, it seems to be much more graceful in terms of how the error increases as we increase the window of our forecasting. And so the climate data set is another one on how we can predict the climate or weather in the coming days. And you can see here that beyond about 180 days, or maybe especially 240 days, the error for LSTM is very high, right? The uncertainty you can also see is really high. But for tensor LSTM, there is still it's a better behaved system. And so there is potential for using tensors for long-term forecasting. Yeah, I mean, I won't go into this result, but it turns out that tensor train RNNs have a universal approximation result of finite order. So any given rank of the tensor train and given number of hidden parameters, you can tell what is the approximation error, and you can kind of specify how that depends on the smoothness of the function and the order of the polynomial interactions we are using in our system. And no such result exists for recurrent neural networks because they don't have this property of universal approximability given a finite order network. So yeah, you can also use tensor formulations for multiple modalities. So you have image and text. The question is, how do you pull together the features extracted from image and text efficiently? Without going into details, there is formulations of taking together the image feature tensor and the text vector in this case, and doing sketching in efficient ways that can give rise to state-of-the-art results in visual question and answering. So very quickly, I want to show how tensors are also applicable for extracting topics from documents. In this case, it's unsupervised learning because we only have a corpus of documents, and from that can we extract what the topics are. For instance, in this document, the topics talk about government, information technology, politics, and so on. So the latent Dirichlet allocation is the popular model for learning this. And we had a framework that looks at co-occurrences of words in the document, right? So what are the number of times different words co-occur? And if we look at triplets of different words together and we do a decomposition of the tensor, it turns out we can find topics efficiently. Since I'm running out of time, I will skip the details here. But this algorithm is available on SageMaker. That's the machine learning platform at AWS that we've recently launched. And so you can go ahead and run that. And it turns out that the tensor algorithm is much faster for training topic models compared to some open source frameworks like Mallet. And this is available on SageMaker, so you are welcome to go and try it out. So just a short word about what SageMaker is. SageMaker is a new platform that we released that allows you to take machine learning from a concept to production very seamlessly. So there is no setup required for infrastructure, right? So if you want to do multi-machine training, you can do that out of the box. If you want to change instances, you can do that seamlessly. You want to host multiple models, do A/B testing, deploy them in different forms, and do model management, you can do that very easily. And so this does a lot of heavy lifting when it comes to DevOps, so you can focus on the machine learning aspect, which is where a lot of new innovation needs to be done, right? And so that's what SageMaker is very useful for. And there are many other algorithms on SageMaker in addition to the latent Dirichlet allocation that I recently mentioned. And of course, there's the whole stack of machine learning solutions we have on AWS. SageMaker is the platform. There are a number of managed services for computer vision, speech, language, and there are a number of frameworks we support on AWS. And of course, we have different forms of instances you can use. Yeah, so to conclude, I showed how tensors now give you another handle to deal with data dimensionality, right? So you can naturally encode data of any arbitrary dimension through tensors. You can now have neural network architectures with tensor algebraic operations that could lead to much more compact networks, that could lead to better accuracy, that can lead to new frameworks for even unsupervised learning like topic modeling. And at the same time, there's a lot of new innovation to be done in terms of how we can scale up tensor operations more efficiently on different hardware platforms. Thank you.
Thank you, Anima, for that excellent talk. So we have time for questions if you would like to come up.
Hi, excellent talk. I was familiar with SageMaker, didn't realize that so many of these features are involved in it. You mentioned using tensors for forecasting. Do you believe that it would be effective for biological signals where sometimes the shape and rate, more so than just the history of it, you're trying to make predictions based on that too, like probably ECG signals or pedometer, stuff like that?
I mean, I don't know the specific details of that application, but the more dimensions there are, right, it can only help you as long as there's enough data, enough good quality data. So you can naturally also incorporate that into there are a few more orders of tensors, and so it becomes a natural extension.
Okay, awesome, thanks.
So we've been using tensor decomposition for some of our work, and I mean, it's been really great. So it's really nice to see that there's this focus on trying to make the computations more efficient under the hood. On the tensorized neural networks, you showed using a Tucker decomposition and Tensor-Train. Did you find that they had broad benefits over, saying, using a CP decomposition? And when you go to choose the rank, do you have any heuristics you use to try to do that beforehand, or is it just a hyperparameter search?
Yeah, so I mean, the Tucker one is more general than CP, right? So the CP is kind of like the core is like a diagonal tensor, right? That's the, and so it turns out the CP was too limiting in this case. So the Tucker gives you much more, it's not as constrained, and that helped. But yeah, in terms of hyperparameter search, it was, there wasn't, I mean, we did use like the pre-trained networks and try to compress that and try to use that as the initial rank. Okay. And so that way, at least we had one good setting, right? You can get better after that. So.
Okay. Thank you.
Yeah. I had a question for you with regard to your tensorized LSTM. So I sort of understand why the error is going down compared to the base, but how about the variability? I've noticed it was very tight over time and sometimes unstable. It would go up and down. Is there any way you could explain that in like layman's terms without going too much into math?
Sorry, go up and down in the
so like
base.
the spread was sort of increasing, then decreasing, then increasing again, and in the baseline it was sort of like going, in the natural directions.
Yes. Yeah, so I mean, yeah, so I don't think we have a good explanation for that right now because, the uncertainty aspect of it, right, so far we didn't kind of look more closely into that. I mean, one way could be to do more autoregressive or those kind of models explicitly try to get a handle of uncertainty. I think that will be a better way for us to study that.
Thank you.
I'm afraid we should take that last question offline so that we can stick to schedule. Thank you once again, Anima.